Hey everyone, and welcome to our video on stacks and queues. This is our third data structure that we're covering. So let's get right into it. Stacks and queues are a linear data structure where the order matters. The stack is the last in, first out, and a queue is a first in, first out. So a stack and queue has no wasted space. You cannot access indexes directly, and you cannot search the data structure. Well, technically you can search the data structure, but if you're searching a stack or queue, you're doing something wrong. So let's talk about stacks and queues. First, let's do our stack. So when you think of stack, you want to think of a stack of pancakes. So this is our stack. So the last in is the first out. So we have a stack of pancakes. So this is the first pancake made all the way at the bottom. New pancake gets made, gets thrown on top. New pancake gets made, gets thrown on top. New pancake, and then the last pancake, which is steaming still, right? This one just freshly made, it's still giving off a whole bunch of steam. And then someone comes and eats your pancake. So the last in is the first out. What was the last pancake made? It was the one that's steaming, the hot one. That's the first one that someone's going to come grab. That one gets eaten. And then someone comes and grabs this one. And then someone comes and grabs this one. And then this one. And then this one. And then this last pancake was the very first pancake made, and it's the last pancake to be eaten. That's the stack data structure. Then we have a queue data structure. A queue is the first in, first out. So let's go back to our blue. So the queue goes like this. And we always want to draw the directions of our queue. So the first person to come in gets in line, and then the next person, and 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 they're all in line, waiting to buy some groceries. They're all just minding their own business, all of them. Cool, they're in line. And then all of a sudden, they start taking people. So the first person gets served. They're gone. Now you're the first person in line. And then you get served. And then this person's the next person in line. And then they get served. And they're the next person in line. And then this person gets served. And now they're the next person in line. And then they get served. And then this last person is then the next person in line. And the line is empty. So it is first come, first serve. First in, first out is the queue. So when you think of a stack, you want to think of a stack of pancakes. And when you think of a queue, stack of pancakes. And when you think of a queue, you want to think of a line, which is what they call a line in the UK. They'll call it a queue. So the stack and the queue, very easy to think of. Now let's see what it looks like as far as our code goes. So first we want to start with our include stack, and then within main we have stack, and then whatever type we want to make it, we're going to make our stack of type int, and we'll call it my_s. So let's go and create our stack by doing that. So we went and created an empty stack, and then we're telling it to push. So let's do a whole bunch of pushes. Let's push 4, and then we'll do push 5, and then we'll do push 6, and then we'll do push 7, and then we'll do push 8. So we'll do all those, and then we'll do some pops. And then we'll do dot pop. And then we'll do dot push 9. So let's walk through these. And we'll highlight the ones that we've completed. So we've completed it. Now let's add 4. So we add 4 to our stack. And then we've completed it. And then we add 5. Now we've completed 5. Now let's add 6. Now we've completed the 6. Now let's add 7. Now we've completed 7. Now let's add 8. Now we've completed 8. Now let's pop. Erase 8. Now completed pop. Now let's push 9. Now completed 9. And then we have more lines of code, ... And then we have pop, my_s.pop. So then we pop the 9. And then we have cout my_s.top. So top is going to return to the user the top element. And the top element in this case is the 7. So it is going to return back to the user the value of 7. That is the stack. Now let's get into our queue. So very similar, we have include queue. So then of course within main is the rest of our code. So we've executed that. Next we have a queue to be created. So we're going to create a queue. Our queue goes this direction. We have done that line of code. Now let's do a whole bunch of pushes. So let's do push 0, push 1, push 2, push 3, push 2, push 1, push 4, dot pop. Okay. So let's see what all of this looks like. First we have our push 0. So 0 gets added to the queue. We are done with that line of code. Then we add 1. Done with that line of code. Then we add 2. Done with that. Then we add 3. We've executed 3. Then we add 4. And then oh, I'm sorry. Got carried away there. After 3, you add 2. Executed 2. After 2, you add 1. Executed 1. After 1, you add 4. Executed 4. Now we have pop. Pop is added. It's going to delete from the right. So it's going to remove the 0. And then we have executed pop. And then we have pop again. So we're going to remove the 1. So popped again. And then we have front. So front is going to return the value of 2 back to the user, because the front item is the front here, while the top item is on top for the stack. So we realize that the stack utilizes the top and the queue utilizes the front. And that's another way to look at it, that we have our structure which has an item on top, and then we have a structure which has an item on front. Because the front, this structure goes this direction, the front would be all the way on the right side. Cool. So that's what the data structures look like. Again, like a stack of pancakes. First pancake made. So stack of let's make it more like a plate. Here's your big plate. And the first pancake made is the last eaten. So here's your first pancake. And then they come in, they drop the next pancake. And then they drop the next pancake. And they drop the next pancake. And the next pancake. And of course, everyone comes around, they grab this one first, then that one, and that one, and that one. And this last one's soggy because it has been there for so long. And then your plate is gone because those are all the pancakes. And then lastly, you have your queue. Again, like a line, first come, first serve. First person, second person, third person, fourth person, fifth person. And then they serve the first person, they serve the second person, they serve the third, they serve the fourth, and they serve the fifth in that order. Now let's talk about some speeds. So the speed to access an element, you cannot do that. You cannot access the 5th element directly in this data structure. The speed to insert is an O of 1. The speed to delete, which is just popping off the top item or the front item, is an O of 1. And the speed to search is an O of n, technically, but you should not search, because the only way to search for an item is by going through, deleting every item, and saving it in another structure until you find your item, and then at the end copying all the items back. So it is very expensive. It would be a 2n operation, which then becomes an n, but it is expensive to search, and if you're searching with a stack or queue, you're doing something wrong. Here's help, and here's some code. So let's start with our IO stream, and then we add the stack and the queue. So using namespace standard, then of course the student class that we've used for the previous data structures. So we'll walk through it very quickly. We have some private types. In our public types, we have a default constructor, a parameterized constructor. We have 4 getters, and then we have the overloaded operator for the insertion. This allows us to print entire objects in a format of our choosing without using some sort of print function. I can just print it with the insertion operator, which is preferred. So first we're going to create a stack of a primitive type, and then we're going to create a queue of user-defined type. So first we have our stack of type string, and we're going to create 2 of them. We're going to create my stack and then a copy stack, and we'll explain why we use that. So then we're just going to push a bunch of items onto our stack. So push the first item, then we're going to push the second item, push the third, push the fourth, push the fifth, push the sixth. Keep in mind that the sixth item is now on top and the first item is buried at the bottom. So that is how our stack looks. Next, we are searching. So the first thing I want to do is I want to take everything in my stack and I want to copy it to my copy stack. And the reason being is the only way to search through a stack is by deleting every single item in the stack, searching for that item. So what I have to do to search through the stack is check the item, check if it exists, or check if it's what I'm looking for. If it's not, pop it, go to the next item. If it's not, pop it, go to the next item. Continuously do that until you find the item. Once you've gone through the entire for loop searching for your item to see if it's found, you then have to take all the items from your copy stack and then copy it back into your original stack. So your copy stack is just used as a filler. Your copy stack holds all the items, and then you search through it, and then you take all the items and you copy it back. Of course, you could just iterate through your copy stack in this for loop. You could do that, but I wanted to show you guys how it works with using the top and the pop. So looking at this for loop now, we have int I equals the size and I is less than 1. And the reason why we're doing it flipped is after each pop the size can change, so it can't increment up as it increments down. So when it comes to stacks and queues, we have to do a for loops reverse. It's pretty interesting. If you do it the other way, you can see why, because it'll make a mistake, and it's kind of interesting to find out. So if the my stack top, which right now the top is going to be this item here, if top equals my entry, then cout found. If not, then we are going to pop the item, right? And then, I'm sorry, I guess I should put this in an else, because if you find the item, then you should also break. So let's optimize this a little bit as we're going on. Let's assume that we found the item, then we also want to break because we found the item. And let's make it an else. If we did not find the item, then we can pop the item. So, and then after, so if this is our top item, it is not found, so we pop it. Now this is our top item. Does it equal what we're looking for? No, it doesn't, so we pop it. Now this is our top item. Does it equal what we're looking for? No, it doesn't. We pop it. Is this? No, we pop it. Is this? No, we pop it. And is this? No, we pop it. So the item was not found. So the item we were looking for does not exist. So what we could do is we could create a boolean. So we'll create a bool trig equals false. If the item was found, then we'll set the trig equals true. And then at the end of this, we will do if not. Let's change this to found. By the way, I spelled trig wrong anyways. If not found, then we can cout. Wow. Did it again. Not found. That works for me. So if the item isn't found, then it will execute, or it'll show that we did not find the item. Which in this case, my entry does not exist, so it will execute not found. And then of course we copy all the items back. And then the way you remove is of course with the pop item. So this is printing and removing. So I just want to show you guys how to use the myStack.top. This prints the items, and then of course the pop so removes it. So even though this is the remove section, this is going to go through. It's going to view the top item. It's then going to view it and then pop it, and then view the next one and then pop it, and then view the next one and pop it. So this is showing you how to show every item in the stack, but it's also popping every item in the stack. So it's removing an item as it prints it. Next, we have the creation of 5 objects, and then I'm creating 2 queues, a copy queue my queue, and then a copycat. So then I push all my 5 objects. So here's my 5 objects, and then I push my 5 objects. Must have not. Oh, is there one too many of these? Is that why it's giving me all these underlining errors? Yeah, it is. So create the 5 objects, push the 5 objects, and then of course do the same thing for searching, but this time I'm searching by the campus-wide ID. So take my queue, assign it to the copy queue, and then I can go through and I can safely search everything and pop everything off of the queue. So searching if something's in the queue by doing myQueue.front and then the campus-wide ID. So searching the front object. So of course when you push into a queue now. So we're pushing this item to the front, then the B goes behind A, and so on and so forth. So it would look like this, to where E is the last item, and then D, and then C, and then B, and then A, going, of course, this direction, going that direction. So when we call front, we're calling it on the A object. So first we're checking if A's student-wide or campus-wide ID equals the following. If it does, then we found the student. If not, then pop, so on and so forth with copycat, and then that's how you remove. So now let's save it. Let's build it, and let's run it. Of course, we could do the optimization to this search that we did above. I just wanted to show you guys. So it's giving us an error. Where's our error? There. We didn't put a semicolon, so save it, build it, run it. So first is the search. It's searching for my entry, and that item is not found. It is then going through our for loop to do a top of everything and then a pop of everything. So this is going to print everything that exists in the stack in order. So it's first this item, and then this item, then this item, then this item, then this item, ending with entry 0. And then we get into our student. And the first thing we get into is our for loop. So it's checking for the student. So found student Andy Bernard by the campus-wide ID. So we found him. And then the last thing we're doing is we want to check the speeds of the stack. So I'm going to clean it up by doing a cout endl right here, and then we're going to save it, build it, print it, and then we're going to talk about our speeds just to clean it up a little bit right here. So for the speeds, for our average case and for our worst case, the numbers are the same for everything. So access is O of n, search is O of n, insert is O of 1, and delete is O of 1. So again, your access for this is also kind of like nulled out, and same with your search. If you're searching with a stack or a queue, you're doing something wrong, and you don't want to be accessing it all with the stack and a queue, so you're also doing something wrong. So something to note that the stacks and queues, the insert and delete is the O of 1. They have a specific purpose. If you're just utilizing a stack and queue because you think it's the right data structure, you're probably wrong. It has a specific purpose. And what I mean by that, you're probably wrong, is what I mean. If you're just going off a whim and picking a data structure and you go with a stack and queue thinking that that's a good linear data structure for you, that's when I'm saying you're wrong. It's used for specific tasks. So if you know when to use it, then you'll know it when it's handy. Otherwise, you don't want to use it when you can use a vector or a linked list. So just something to think about. And we'll see.